Good afternoon, everyone. Today, I'm here to talk about evaluating the size effects of a deep life of steel alloy using a statistical SN model with highly stressed volume and surface. My name is Julian Marques. I'm a postdoc researcher at CTU in Prague. As engineers, you usually need to perform fatigue tests of real scale components. We are interested on the SN curve. A common approach, because it's very, however, it's very costly and can also time consuming. Then a common approach is replace the real components by standard specimen, small specimens. And the fatigue results can be extrapolated by an empirical model or a statistical model. And this is our main goal: investigate the size effects using a statistical model for different high stress volumes and surface. This is the overview of my presentation. I will start with Castillo model, a statistical model, and highly stress volume, the theoretical background. Then our proposed model for size effects. Then I will verify our model using experimental data, fatigue data, and finally I will point out some conclusions. Let's start with Castillo model and high stress volume. In 2009, Castillo proposed a method, a fatigue model, derived based on dimensionless variables. I will not go into mathematical details. I will show the probability of failure, or it's known as cumulative density function, of the general model with fixed asymptotes. As we are interested in the regression equation, here you can see it in yellow for constant stress ratio, minimum and maximum stress. It depends on C parameters. These parameters of the model follow a Gumbel distribution, can be determined using maximum log likelihood. Here, the log likelihood is a summation of any terms, and its maximum is subject to these constraints. So we can obtain the parameters of the model. Here we need a non-linear optimization to obtain these C parameters. Also, in 1985, Castillo proposed also a model for different lengths of wires and cables. They state that longer cables has a short lives, and also here in the SN curve we can see that the distribution is narrow for the short, for the long cables. Also, the model considered is based on the weakest link principle, which considers fatigue life identical, distributed, and also independent. Here is the relation between the short and longer cables. And here the Weibull, considering Weibull distribution, is the probability of failure of a longer cable. Not only models, fatigue model for different lengths are available on literature, but also for different volumes. It's based on highly stressed volume, the theory, and these volumes are subject to a fraction, for example, 95% and more of peak stress. And this concept, this high stress volume, was originally proposed by Papuga in 1960. And he shows here, he found interesting, because you can see that the fatigue strength decrease as the highly stressed volume increase. We can see an interesting linear relationship in a log-log scale for both is smooth and also notch spacement. So here we can find in the literature fatigue model based on this theory, but anyone, at least we didn't find, is combine the general model, the Castillo general model, with this theory high stress volume. And this is our proposal. So as the length, here we can also see that the volume, the large volume, is equal to n times the small volume. And also for the same for the high stress surface. Here the surface case is studied due to the fact that less volume imperfections usually deal with crack at surface. So, and here, as the Castillo model, we also, this model is based on the weakest link principle, and here is the relation between volumes, smaller and longer volumes. And here, for high stress volume, the Castillo model becomes this one. It's interesting that the main difference is this there. Regression, here is the regression equation for constant ratio, minimum and maximum. And we also obtain similar regression equations for the case of surface. The models also, the parameters of the model is also mathematically derived using the log likelihood. Here we can see including the volume, and here the maximum log likelihood is subject to these constraints, and we can obtain the parameters of the model. Now I will show you some a test case, experimental test case. Let's start with experimental campaign. We study the smooth specimen. We start with solid cylindrical specimen, same material, same bar, same load conditions, push-pull. And also here are the A1 and A2. We can see, for example, the difference is only the size. A2 has a longer central part compared with A1. And here A3 series and A4 series. We also study the hollow specimens, hollow cylindricals, A5 and A6, A7 and A8 series. About our data, these are our data from series A1 to A4. We test about 10 samples for each series. And let me say that since we measure a variation of the roughness and the hardness, we transform the data according to the literature. And also here, A5 to A8 series. Now about the SN curve, or the Castillo model, using Castillo model. Here is the regression curve with probability of failure 50%. As we can see, and as we expected, A1 to A4 are ordered from the top to the bottom of figure because the volume increase from A1 to A4. The same for A5 to A8, except A7. Here we have a different trend in case of A7. It's out of the trend, and we are still studying the reason for that. From now on, I will not consider this series A7 in our analysis. Applying our proposed model. To apply our proposed model, we first compute the volume. Here we can see the volume varying the stress fraction from A1 to A4 series. They have smoothly decreasing, except after 95%. A2 and A4. This is due to the stress distribution on the central part. Here, for example, A4 series, 95%, and the stress distribution with 96%, decrease a lot. So also we obtain very similar results in case of hollow specimens. Here for surface, they are in a different order. And now the next step, using these values, volumes and surface, we check if our model was in agreement with our data. What is important here is because we test based on a statistical test. Okay? But what is important here is the acceptance ratio that is above 5% significance level, and almost all series are above 5%, except A5 and A1 with 95% in case of volume. And in case of surface, using this statistical test, we have A1 below A5 series. So here, due to these low values, below 5%, we didn't consider joint analyze, for example, A1 volume and A5 surface. We neglect both A1 and A5 from now on. And also we can see that, if you remember, we can see that A1 and A5 series, they all are very small volumes. That's why it might be a sort of below a sort of threshold. And here our test case verifying our model without A1 and A5. We can see that all values are above 5% significance of level for any stress fraction. And here for the case of surface, the same for the case of surface. Since we could choose any stress fraction and also volume or surface, to show you an example of our proposed model, we chose a 95% volume. And here is the regression equation using 95% and volume 95%. And it may be extrapolated here. It is important because we can extrapolate for large specimens. Of course, we need to check our model about the hypothesis. Now, the regression curve. Here, applying the regression curve, for example, A2, A3, both have very similar volumes, so we can expect that they overlap. And here, about the hollow specimens, A6 and A8, in general, all have demonstrate a very good fitting, but as engineer, we don't usually we don't want 50% of probability of failure, and that's why we verify for different probabilities, and also to check the distribution of the data. And here we can see different probabilities: 2.3% and 50% and 97.7%. For the case of A2 series, A3 series, and also A4 series. And regarding the hollow specimens, A6 series and A8 series. It's interesting because here we can observe that all data are above the 2.3% probability, and this is very interesting for each series. The data for each series, we see that the lines are the data are above the 2.3% probability. Now about my conclusions. So we introduce a fatigue model for size effects, and this model extends the general Castillo model to the case of high stress volume and also surface. It allows us to extrapolate the ascent curve for large specimens, and the model shows a good agreement when applied for specimen series, our experimental data, with different volume and surface. Thanks for your attention. Special thanks to University of Ferrara and CTU Global Postdoc Fellowship for providing funds.